All right, welcome to Math372 Complex Analysis. This is day 4. We are going to talk about triangles today. And if there is a lot of time at the end, which I'm not quite sure, we will actually get to a circle. Okay? So the point of today is to start learning how to integrate along curves. Is to start building up the prerequisites we're going to need. And we're going to start with really simple shapes. Instead of a triangle, you could try to develop the theory through squares and rectangles. Triangles actually fit together nicer for a bunch of things. The other thing that we are going to consistently learn in this class is that notation is, or at least nomenclature, is a little bit different in this class than it is in other things. So in Calc 1, you talk about the antiderivative or the integral. In complex analysis, you talk about the primitive. So if you have a function, the primitive is basically its antiderivative or its integral. So big F is, we'll say, a primitive of little f if big F prime of z equals little f of z. And of course, primitives are not unique. I can change this by an arbitrary constant, and it's not going to really matter. So a really good example is, let's say f of z equals the sum, and it goes from 0 to infinity, of an z to the n, and it converges absolutely if the absolute value of z is less than r. Does this function have an antiderivative? Okay, what would you guess? I'm seeing people nod their head, so I will assume that this means integrate term by term. Right? So it'll be the sum, n goes from 0 to infinity, of an over n plus 1 z to the n plus 1. Do we have to worry about dividing by 0? No. So this is fine. Do we have to worry about the radius of convergence? Well, yeah, it's still going to converge if the absolute value of z is less than r, because I'm just making each term either smaller, or if n equals 0, I'm not changing it, and one term doesn't matter. So this will still converge absolutely if the absolute value of z is less than r. So what's nice is if we have a primitive, integration is actually very easy. So I'm not going to go through, good luck with the desks, I'm not going to go through the details of the calculation, but let's say big F prime equals little f. And I want an integral along some curve of f dz. This will be f at z final minus f at z initial. And the proof is basically the change of variable formula from Calc 3. And so you just go through, you parameterize the curve, and because we have an antiderivative, you're fine. If there were a lot of physics students in here, I would talk about a potential function, and you're integrating basically the gradient. And you're basically looking at the potential difference. What would you love to be true in this formula? Yeah. If z final equals z initial, then we get 0. I can't be excited and write an exclamation point because it could be mistaken for a factorial. So I will contain my excitement. But this is really nice. If you have a function that has an antiderivative and you integrate along a closed curve, you get 0. So what we can now do is we can now try to look at various functions and do some integrals. And so I'm going to do the most important integral in the class, and I'm going to do it directly. So as an example, let's consider the integral over gamma of z to the n dz. Gamma is the boundary of a disk of radius r about the origin. So I can write z as r e to the I theta. dz is going to be I r e to the I theta d theta. And so now we'll have that our integral is equal to theta goes from 0 to 2 pi. I'm going counterclockwise. I will have r to the n e to the I n theta times I r e to the I theta d theta. And so when I look at this, it's the integral theta goes from 0 to 2 pi. Well, let's pull out the constants. I have an I that I can pull out. I have an r to the n plus 1 that I can pull out. And I have an e to the I n plus 1 theta d theta. And now things get a little bit interesting. If n equals -1, then I'm just integrating e to the 0. E to the 0 is 1, so I'll get 2 pi. So this answer is going to be 2 pi I if n equals -1. If n is not -1, if it's any other integer, then I'll have like e to the maybe 4i theta. And then when you write that out, I'll have cosine 4 theta plus I sine 4 theta. And since I'm going through an integral number of periods, it will be 0. So I get 0 if n is any other integer. Does this seem surprising? Does z to the n have a primitive? Except when n equals -1, z to the n has a primitive. When z equals -4, there is a primitive. Now, the primitive is not defined in the entire region. It blows up at the origin, so you have to be a little bit careful. But it does have a primitive. What about when n equals -1? Does 1 over z have a inverse? I'm sorry, does 1 over z have a primitive? Or what would you like it to be? You'd like it to be log. So we have to worry as to what exactly is the log of z. And if I write z as r e to the I theta, is the log of z the log of r plus I theta? Well, I have now different choices of angles. They would give me the same z, but they would have different logarithms. So the complex logarithm is actually a lot of work to define and do it properly. What this example shows you is that when n equals -1, something interesting is happening. It's related to the fact that 1 over z doesn't have that nice antiderivative. Z squared goes to something like z. Z goes to constant. 1 and 0 both go to 0. Oh, that's like a double alignment. And we're missing that there's no function that goes nicely with 1 over z when we're looking at these antiderivatives. So a huge amount of the subject is going to come down to this. We can integrate z to the n along any nice circle. We can then probably integrate linear combinations of z to the n's. So if I give you some kind of sum of a n z to the n, and I'm integrating about a circle, well, hopefully the integral of the sum is the sum of the integrals, and I just do it term by term by term. And the only term that matters is the -1 term. And this is where the power of complex analysis is going to come from. All we need to do to understand integration is look at Taylor series expansions, look at the -1 coefficient, and that's where the action lives. So sometimes people no longer call these Taylor series. They sometimes call them, I think, Maclaurin series, or Lorentz series, if you include negative terms. I will probably still call it some kind of series expansion. But this is the main idea. This is the integral we want to do. OK, so let's start thinking about how we can do integration. So the first thing is, I said we had to choose what kind of curve we want to look at. And I want to look at triangles right now. Triangles fit together nicely. If I give you a region, I can just choose 3 points. That's a triangle. And then I can choose another point, and I can keep building it out like this. If it's a square, it's a little bit harder as you're filling out and trying to break a circle into squares. You can do that, but you can't necessarily use the same previous point. So if I give you a curve like this, and I have a square like this, I'm having some trouble now. Let's say this is actually on the boundary here. I can't choose another point like that. But if I'm doing triangles, I can choose another point like this, and I can keep dividing things up very nicely. So triangles fit together very, very well. So the first thing we're going to do now is we're going to prove Goursat's theorem. I want to make sure I get the conditions correctly. OK. So come over here. Goursat's theorem. Let f be holomorphic on an open set omega that contains a triangle T. Then the integral over T is 0. Okay. So basically, if I integrate a holomorphic function along a triangle, I get 0. This is a little bit different than what might happen in real analysis. And so later, we'll do an example afterwards to just go through the details and actually just check that this works. To some extent, maybe we should even check it right now. Choose the function z squared, go through and see that it seems to work. Then what function should we choose? Let's choose maybe z bar and see what happens. All right, proof. I may not be able to draw circles, but I can at least draw triangles. All right. Triangles have a lot of nice subdivision properties. One thing that's really good is I could take the halfway points of each of these. And without loss of generality, I can always orient my triangles so that one side is along the x-axis. And now, I cut the triangle like this. What can you tell me about these triangles? They're similar. So for instance, if this is angle alpha, and this is angle beta, and this is angle gamma, what other angles can we say? Well, this line is parallel to that, so this has to be gamma over here. Right? This is parallel to this, so this has to be alpha. This would then have to be beta. If this is gamma and this is alpha, what does that have to be right there? Beta, because it has to add up to 180. Since this is parallel to this, this has to be alpha up here. Right? And then, so which one is this going to be over here? That's going to be gamma. This then has to be beta up over here. And now I've got I've got alpha, beta, so this has to be gamma over here. I've got gamma, beta, this has to be alpha. So all the triangles have the same angles. It's actually sufficient to just show that each triangle has 2 angles in common with all the others. We also know things about the sizes. So not only are they similar triangles, but I think they are equal triangles. So is that correct? Yes, they're equal triangles. So things are extremely nice. And again, this is a good property of triangles that when we're subdividing, they have nice things. What we're going to do is we're going to let T sub n be some of the triangles at stage n. So at each stage, we're going to subdivide the triangle, then we're going to subdivide one of the divisions, and we're going to subdivide one of the divisions. And for each one of them, we're going to choose a special triangle. There may be multiple triangles that we could choose. And the goal is we want to show that this integral equals 0. So we'll show that the absolute value of that integral can be made arbitrarily small. And if it can be made arbitrarily small, the only way that can happen is if it's 0. If I do the integral of f along this triangle, how does that compare to the integral of f along all of these subtriangles? They're equal. Why are they equal?
Because it's going to cancel.
It's going to cancel. Excellent. So when I go through this one, I travel on this triangle, this side going down, but on this one I travel that side going up. All the internal sides are hit twice in opposite orientations. So the integral over the big triangle is the same as the integral over the 4 smaller triangles because things cancel. So if I want to know how large is this integral is equal to the sum of those 4 integrals. So the absolute value of this integral is equal to the absolute value of the sum of the 4 integrals. It's actually kind of nice we're now going to use the triangle inequality. It's just a coincidence in language right now. But then the absolute value of this integral will be less than equal to the sum of the absolute values of those 4 integrals. So at least one of those 4 integrals has to be at least a quarter of f, of the integral of f in absolute value. Because if all 4 of them were smaller than a quarter, then when I add them, it'll be smaller. So what you can do is the integral over the triangle of f dz in absolute value is less than equal to the sum, I goes from 1 to 4, the integral, we'll call it t sub 1 for the first level of cuts, comma I, and then we'll change this notation in a moment, f dz. Why is this horrible notation? I have done something that you should never do in a complex analysis class. Yes. I used I as an index of summation. Okay? Thou shalt not use I as an index of summation in complex analysis. If you really want to make a mistake, this is one of the best ways to do it. Okay? You can't use I anymore. So what we can do is we can use M, we can use K, we could use L. Do not use I. So we know that the integral over this, and we might as well call this maybe triangle T0, is less than or equal to the sum of those. So at least one of these integrals must be at least 1/4 of that integral. Right? So there exists an M such that the integral over T0 of f dz in absolute value is less than or equal to 4 times the integral over T1m of f dz in absolute value. Right? Because if this was not the case, then when we add them all up, we would have trouble. We could take whichever one is maximum, or just one of them. And then we just lather, rinse, repeat. So we choose one of these triangles, then we divide up T1m. So divide T1m into T2m, m in 1, 2, 3, 4. And then lather, rinse, repeat, the shampoo instructions, right? You just keep doing this. And you get a chain of triangles. And now what you'll have is the absolute value of the integral over the original triangle of f dz is going to be less than or equal to 4 to the n integral over some triangle tnm of f dz. And we have the initial triangle T0 contains T1. I don't know which m it should be, so I'll just have to call it maybe m1. Contains T2, m2. Contains T3, m3. Contains ... Because I keep subdividing. And at each moment, I always look to see which triangle do I want to contain. And at least one of the triangles will work, because if all of the triangles have small absolute values of their integrals, then I can't get to what the integral should be. What can you tell me about the sequence of triangles?
They're getting smaller.
They're getting smaller. So let's be more specific than getting smaller. How small are they getting?
Oh, they're getting divided by half.
Right. Each triangle is half the size of the previous. So we now have a sequence of compact sets. The diameter of each one is half the diameter of the previous. And we have inclusions. So in the limit, what is the triangle going to converge to? It converges to a point. So this is one of the places where we are using results from real analysis. So the sequence of triangles converge to a point, let's call it Z0. So there is some point that they will converge to. Is that point on the boundary of one of the triangles? Yeah, maybe, right? Imagine we always choose the bottom left corner. I'm just in the bottom left mood today. And if we always choose the bottom left corner, it will converge to this point. I could, of course, be thinking about this point over here. You can make it converge to anything. I can't say whether or not the point is in the interior of the triangles or it's on the boundary. This is why we were very careful and say f is holomorphic on an open set omega that contains the triangle. So I have differentiability not just on the triangle, but a little bit further. I do not know where that final point Z0 is. It could actually be on the boundary of the original triangle. Okay? So now let's look and see what's going on. So the diameter of T n plus 1 m sub n plus 1 is equal to 1/2 the diameter of Tn mn. The diameter is going down by a factor of 2 each time. Another way of looking at it is the diameter of Tn mn is 1/2 to the n the diameter of the original triangle. So what this is telling us is that the triangle is getting extremely small. So if I'm integrating and I'm varying my point along the boundary of the triangle, I can't move that much. Okay? What do you think would be good to use at some point in the proof? It would probably be nice at some point to use the fact that f is a holomorphic function, right? What does it mean for a function to be holomorphic? It means it's differentiable. So since f is holomorphic, at z0, we have f of z is f of z0 plus f prime of z0, z minus z0, plus c of z times z minus z0, where this goes to 0 as z goes to z0. So this is what it means to be differentiable at a point. F of z minus f of z0 over z minus z0 is going to converge to f prime of z0, and then plus a little error that goes to 0. And I'm just writing the error as c of z times z minus z0. If you want, we could put a z0 subscript on c to remind us that this is a function coming from the point z0. Okay, so if I want to integrate my function f over a small triangle, it's the same as integrating these three functions. This function is very easy to integrate along a triangle. Why is this function easy to integrate along a triangle? It's constant. What's the integral of this function along the boundary of the triangle?
Perimeter times 0.
It's 0. Is there a primitive? Is there a function that has derivative f of z0? Yes, z times f of z0. This has a primitive. And the strange result in complex analysis is if you have a primitive, you integrate to 0. And the reason is the dz is a little bit different than the dx. What about f prime of z0 times z minus z0? Is there a primitive for this? Yeah, f prime of z0 times z minus z0 squared over 2. So this whole part has the primitive f of z0 times z plus f prime of z0, z minus z0 squared over 2. So integrates to 0 along all the tn mn's. Okay? This is why we've been very careful that when we have our absolute values, the absolute values are outside the integration and not inside the integration. The absolute value function does not have a nice derivative. We don't want to work with something like that. What function has derivative absolute value of z? But what function has derivative z? That we can do. And so here, if we now integrate over a triangle, the integral of f of z over a triangle is going to be 0 plus the integral of this over a triangle. So it all comes down to how large can the integral of this be over a triangle? Well, this is tending to 0. And how big can z minus z not be? Yeah, basically it's at most the diameter of the original triangle divided by 2 to the n. So it's getting very small from that. And now we can also say, when we integrate this, we'll then have the size of this times the size of the perimeter. And the size of the perimeter is going to be like 1 over 2 to the n times the perimeter of the original triangle. So I'm going to have a 1 over 2 to the n from the perimeter. I'm going to have a 1 over 2 to the n from the diameter. That's going to give me a 1 over 4 to the n, which is going to perfectly balance the 4 to the n over here. And what will be left over at the end of the day is we'll have a little bit of c of z. And that's going to be tending to 0. This is where it would be really, really nice to have a third blackboard. Okay? So I will erase this part over here. I don't think we need this part anymore. When we get to the proof that takes a week to do, that will be interesting. And we may actually rotate the desks. So now what we have is the integral along t naught of f dz is less than or equal to 4 to the n, the integral of f dz over tn mn. And then that's going to be less than or equal to 4 to the n. Then I will have a 2 to the negative n diameter of t0. And then I'll have a 2 to the negative n perimeter of t0. And then it'll just be times the maximum value over tn mn of c of z in absolute value. Well, this tends to 0 because it's converging to z0, and by the definition of holomorphicity, it has to go to 0. Otherwise, our function wouldn't be differentiable. And now the 2 to the negative n's cancel the 4 to the n. We have a constant over here, and so this tends to 0 as n goes to infinity. And that finishes the proof. So we've now shown that if we integrate a holomorphic function along a triangle, it's 0. Okay. Any questions on this? This is, I think, our first good long proof. We did a long proof that the derivative of an analytic series expansion is just what you would expect. I'm not going to call that a good proof. It's a nice proof. It's a 3 epsilon proof. It's fun. But this is not really a surprising result. This is a somewhat surprising result.
So we already know that if a function, if a holomorphic function has a primitive and we integrate it along a curve that it's 0, so
yes.
The difference in the assumption of this is that we don't require the function to be primitive?
Correct. We just know that the function is differentiable. We do not know that it has an antiderivative. And again, I hate this part of the semester because I do not know what I'm allowed to use. And I have to keep looking at my notes. At what point does the following knowledge come into play? Right now, we do not know these things. The big theorem is that if you're differentiable once, you're differentiable infinitely many times, and you have a series expansion, and therefore you have a primitive. So eventually, we will learn that this is much ado about nothing. But right now, this seems interesting. Now, some of you may have a bias against triangles, and you prefer rectangles. Corollary. True for rectangles. So does anybody know how to prove it as an immediate corollary that it's true for rectangles? Yeah, like the Zorro slashing. There is another proof. Anybody know the other proof? Yes, exactly. The other proof is you could go like this. Or if you really wanted to, you could go like this. Right? That would, there's lots of proofs. They're all essentially the same. You chop it up. It's 2 triangles. And then you just apply Goursat twice. So an interesting question is, what if you knew that the integral over every rectangle was 0? Would you know that the integral over every triangle is 0? Does it go in both directions? Could you develop the theory through rectangles? Or must we go through triangles? Okay. So what I want to do now is I want to do an example. And one of the reasons I want to do the example is because it gives a good way to talk about how to do a bunch of examples at the same time. So I want to integrate a holomorphic function over a triangle. I could integrate the function 1, but sometimes it's not bad to start off with something simple, but if you do something that's too simple, you're not going to get a good sense of what's going on. So what's the first legitimate function we could look at? Z squared is a little bit more legitimate than I want. Z, right? We don't have to go all the way to z squared. So what I'm going to do is I'm going to let f of z be x plus epsilon iy. And epsilon will be in -1, 1. And the reason is I can now handle both z and z bar at the same time. And we can hopefully see the difference between integrating a holomorphic function versus integrating a non-holomorphic function. It would be interesting if the non-holomorphic function has the same answer as integrating a holomorphic function, and that basically just in complex analysis, every integral is 0. Right? That's probably not going to be the case. So let's look at something like this. So I want a triangle, and I want to use the same one that's in the notes. So So I want this point to be, I think, 0 over here. I want this point to be 1. I want this point to be 1 plus IA. Along this line over here, what does dz equal? Dx. Along this line here, what does dz equal? I'm sorry? Nope, that's not what I got. I dy. And now along here, I get, this is the line y equals ax. So along here, I've got x plus ia x. So I get over here that dz is dx plus, I believe, a dx. And so now what I want to do is I want to integrate over the triangle x plus epsilon I y dz. So this is going to be 3 integrals that I need to do. So the first integral is x goes from 0 to 1, and along this line, y equals 0. So I'm going to have x dx. Now along this line over here, y goes from 0 to a. I want to make my zeros and a's distinct. I really cannot stress enough how useful it is to be explicit and write down what your variable is when you're doing these integrations. It's in some sense not needed because I have the dx here, but when you have lots of things flying around, if you can make it easier to just glance down and see what's going on, it's worth it. Okay. Now along this curve, what is x plus epsilon I y equal to?
Minus epsilon y dy.
No, I'm just saying, what is the integrand? What am I integrating? What does x plus epsilon I y look like along this vertical line segment? 1. Excellent. It's 1 plus epsilon I y I dy. And in the last piece over here, I now integrate x goes from what to what? X goes from 1 to 0. Perfect. And now x plus epsilon I y, since y equals ax, is going to be x plus epsilon I ax, right? And then it's going to be dx plus I a dx. I'm just making sure. Good. So this is exactly what I have in my notes. One of the things that's worth doing in life is seeing which calculations do you have to do, which ones do you not have to do. When you're looking at this, your first thought is it hard to integrate x dx? No, but I'm going to have to integrate x dx over here going in the opposite direction. They're going to cancel. Right? And so I can actually avoid a lot of this. So if I start writing things down, this is going to cancel out with the x dx over here. Is there anything else that's going to cancel? That seems to be the only thing that I'm looking at that immediately is canceling. All right, so over this one now, I have y goes from 0 to a of this, so that I'll get a plus epsilon I, then it's going to be y squared over 2, so a squared over 2. And this is all multiplied by I. So hopefully I won't make too many algebra mistakes. So do we agree that that next piece is equal to this? All right, then the next piece, we don't have to worry about the x dx. Now we have the x times IA dx. So we'll have plus a IA, and then we have x squared over 2, evaluated at 0 and 1. So it'll be minus a half. We'll have minus over 2. All right, so that's the x hitting those two pieces. Now we have the epsilon IA x dx piece. So that's going to be plus epsilon IA, And then when we integrate x, we get x squared over 2. That's also going to be a negative 1/2. So negative 1/2. And then the last is we have this hits that. So I times I is minus 1. And then we'll have minus epsilon a squared x. So that's going to be plus epsilon a squared over 2, because when we integrate, we got negative 1/2. Okay. So now let's see what we have. So if epsilon equals 1, which is x plus iy, this over here cancels that, and these two cancel over here. So it does equal 0 if epsilon equals 0, if epsilon equals 1. And it's not 0 if epsilon equals negative 1. So you can go through and see exactly what it is. The clearest way to notice is if epsilon equals negative 1, we're going to have an a squared term. And as a is just cranked up to infinity, clearly it's not going to be 0. So there's at least a difference between integrating z and integrating z bar. And by putting in this nice epsilon, we were able to handle the two terms simultaneously. So every now and then it's actually nice to do an example. I remember teaching multivariable calculus or seeing multivariable calculus taught where the students understand the general theory, but if you gave them a double integral to do, they would have no idea how to do it. They understood the theory behind it, but to actually do a calculation. So it's worthwhile to just write down explicitly what is my function, what are the change in z along the different places, and go through and do things and remember to keep things oriented. Okay, any questions on what we have done so far? Okay, so we've now finally got a major theorem, and we've at least shown that the theorem is reasonable. We checked it with z. You could, of course, try it with z squared, z cubed, and these things become harder and harder and harder. And then the question is there a good, easy way to check z to the n? Or is it going to become more and more painful to check something like that without using the general theory? Okay, we've got about 10 minutes left. We could go into, if you are holomorphic, there is a primitive. And we might say a few words about that towards the end of class. But I wanted to give an example of why we care about complex analysis. What motivated the development of the theory. So it is very easy as a theorist to just keep proving theorems for the sake of proving theorems. And if you read a book, the theorems are all so beautifully linearly laid out, and it's so clear that this comes next, and how everything builds. Why did people build the subject? What were they interested in? A lot of complex analysis was developed by number theorists, or by people interested in number theory. And one of the biggest things we want to count in number theory is the primes. The primes are the building blocks of numbers. And then there are a lot of questions you can do. And what I want to talk about today is a question that for years was considered almost a question that you don't ask in polite company. It's not a question you should be asking. Now, of course, that doesn't stop people from asking it. And in fact, it makes some people want to ask it even more. When you think of properties of primes, what property do you think of first? What's the big thing that comes to mind? Fundamental theorem of, not algebra, arithmetic. Right? Fundamental theorem of algebra is a polynomial of degree n has exactly n roots. We will prove that. We will prove that later from the fact that a constant function that's differentiable everywhere is constant. But the big thing we think about is you can take any number and you can write it uniquely as a product of primes if you are willing to say the primes must be written in increasing order. I don't really want to say 2 times 3 times 2 is different than 2 times 2 times 3. Okay? We do not always have unique factorization. And so there are other spaces where unique factorization fails. Example, 2 times 3 is 1 plus the square root of negative 5 times 1 minus the square root of negative 5. So this is 2 different ways of decomposing 6. How many of you have taken algebraic number theory or seen this in an abstract algebra class? Okay. This is a situation where unique factorization fails. Another example is sine of x times sine of x is 1 minus cosine x, 1 plus cosine x. You can actually almost look at like a function equivalent. here's the question. If n is an integer, is n a sum of 2 or 3 primes? So this was a question Goldbach asked. And so it turns out that if n is an even number, if one of the primes is 2, what is true about the sum? It's odd unless the other prime is 2, in which case you're talking about the number 4. Not that exciting. So if n is even, basically we're saying, can we write any even numbers as a sum of 2 primes? If n is odd, what would it mean to write n as a sum of 2 primes if n is odd? Well, one of the primes better be 2. Then that means we're trying to write n minus 2 as a sum of a prime. So that means that n minus 2 must be prime. So it's pretty easy to handle odd n as a sum of 2 primes. The only way it happens is if n minus 2 essentially is prime. Can you write every even number as a sum of 2 primes? We believe it's true. And there's a beautiful method called the circle method that allows us to attack problems like this. Can you write every even number, or I'm sorry, can you write every odd number as a sum of 3 primes? And the way you attack this, or one way you attack this, is using something called generating functions and complex analysis. So let's define fn of z, fn of x, is the sum over all primes at most x of e to the 2 pi I px. If you really want to do things well, you would put a log p weight. You don't treat all primes equally. You bias a little bit, so the larger the prime is, the more weight it gets. But it's a slowly varying weight. It's a small amount of discrimination. We're able to do small amounts of discrimination on this campus. Nothing too major. Okay? If I look at this function, let's look at fn of x squared. That's the sum p1 less than or equal to x, the sum of p2 less than or equal to x, e to the 2 pi I p1 plus p2 x. Now, let's take this function. Somebody give me a large even number that they like.
2048.
I'm sorry, how much? What was your number?
2048.
Yeah, it's not large. So I will do as my even number, but I'll do something closer. E to the negative 2 pi I, you said 2048? Factorial to the 2048 factorial, and I'll take the factorial of that. Right? That's a good large even number. And I want to know, is this the sum of 2 primes? I will now integrate this from 0 to 1. And now, when I look at my integrals, you can view this as I'm integrating the function z to the n about a unit circle. And the only time I get a contribution is if the exponent is 0. So I need p1 plus p2 minus 2048 factorial, 2048 factorial, factorial to be 0. So I can write this as it's a sum over p1, p2 less than or equal to n. Oh, I should be writing n, sorry. And then I'll have the integral from 0 to 1 of e to the negative 2 pi I p1 plus p2 minus 2048 factorial to the 2048 factorial factorial dx. If this exponent is 0, I get 1. If this exponent is not 0, I get 0. So this integral is equal to the number of reps of our number as the sum of 2 primes at most n. And now all I have to do is just make sure n is larger than 2048 factorial to the 2048 factorial factorial. Because if I'm writing it as a sum of 2 primes, each of those primes can't be larger than the number itself. And then that will give me the number of representations of this number as the sum of 2 primes. This is an explicit formula that will tell you not only is it doable, but how many ways is it doable. we have reduced this problem to an integral. Just because I can write an integral down does not mean I can do it. And of course, you don't want to do it for just 2048 factorial to the blah, 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 blah. You want to do it for an arbitrary n. How do you do this for an arbitrary n? So I'm not sure what Professor Goldbach is going to be doing in analytic number theory. This is definitely one of the possibilities that you can look at. It leads to what's called the circle method to handle problems like this. But it reduces things to complex analysis and to some beautiful theory as to why we want to study something like this. So here is a solution. How can we extract information from this? Much harder. If there's time and interest later in the semester, I'm happy to give like a 1 or 2 day sketch as to how you attack problems like this. And here's how you get the main term, and here is the hellish minor error term that you have to somehow deal with, and it takes a while, but you can see roughly what kind of cancellation you need. This is a highly oscillatory function. I'm taking exponentials to very high frequencies. They're going up and down really fast. So I'm hoping that this gives you some idea of why we want to integrate these functions. These allow us to attack problems that we really care about at the end of the day. There's other things, and I'll put up some notes about the Fresnel integrals. There don't seem to be many physicists here. Has anybody heard of the Fresnel integrals? Right. So I will just post that because this does not seem to be a physics-intensive class this year. The Gaussian integral is another. Oh, we actually have 1 minute left. All right. We have 1 minute left. I'll at least write the gamma function. So if you've never seen the gamma function, you should. So gamma of s is defined to be the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx, at least if the real part of s is greater than 0. So you can see that the function converges. You can actually write this as x to the s dx over x. And what's nice about this is if I change x by multiplying by 5, dx over x is unchanged. It's an invariant measure. It's a multiplicative measure. It turns out gamma of s plus 1 is s gamma of s. Gamma of n plus 1 turns out to be n factorial. It's essentially the factorial function slightly shifted. Gamma of 1/2 is the square root of pi. So you can interpret this in some sense as negative 1/2 factorial, the number of ways to arrange negative 1/2 of a person. And this is the normalization constant that comes up when you're looking at the Gaussian. The Gaussian is 1 over the square root of 2 pi e to the negative x squared over 2. This is the Gaussian. And the normalization function here, what I need to have this integrate to 1, is actually gamma of 1/2. So as a nice exercise, do some change of variables. So when you look at the integral of e to the negative x squared over 2 dx from 0 to infinity, and we should really multiply by 2 because you go from minus infinity to change variables and make that look like a gamma at a certain value times some constant. So it's a nice exercise. Try to figure out how that adjusts. This is a good place to stop. If you have not handed in homework, please do so.